This is a talk about board games and how to make computers play them. And despite the talk being about such a subject, I really quite suck at board games. I never played them a lot, and whenever I did play them, whether it was with family or with friends, it never ended well for me. But there was this one exception, this small little board game called Bawo. I've been playing Bawo for quite a number of years. My uncle gave me a board in, I think, 2021, and we've been taking it on holiday with us, me and my family. And I've been playing it a lot ever since, and I've gotten quite good at it. So good that I can more or less reliably beat pretty much any of my family members in a head-to-head game. But that's only my family. The question was, just how good am I? Am I just good enough to beat the worst, or am I actually good at what I do? But before we answer that question, let's talk a little bit about Bawo. Bawo is an inventory management survival horror board game. It moves, it works like this. The game starts in that position, and it works by introducing seeds to the board and moving seeds around the board. There's capturing, and slowly as more seeds are added, the seeds are then distributed. You can see here that I play a very long move, and I seed my front row. The goal of the game is to empty your opponent's front row or leave them with no more legal moves. So just to give you an intuition for the game, if that front row there on the bottom of your screen goes completely blank, I win. You can see more and more beats are introduced, and slowly the next phase of the game comes along when everything becomes empty. Thank you, AV guy. So the game's going on now, and the last seed is eventually introduced, and now the next phase of the game begins, and you can see I start to clear out my opponent's front row. He tries to fight back by building up a little bit more in his front row. I clear it out quite quickly. He does one more move, and in this turn, I loop round and round my side of the board, and eventually I win the game. So that's how the game looks. And I wanted to be able to, get a computer to play this with me for a multitude of reasons. And I knew this was possible because I knew that people had done this before. People create really good game engines to play whatever games they're interested in. For example, Stockfish that plays chess, Elmo that plays shogi, or Patchy or AlphaGo that play Go. If you remember the keynote this morning, that's what eventually beat Lee Sedol at Go. So I've been toying with this idea for a long time. Because having a computer meant I could play against it, and Bawo is quite a complicated game, so teaching it to new people isn't exactly easy, so having a computer I could play against whenever I liked was quite an advantage. It also meant that I could analyze my games and learn from them and become even better. Like in chess, you can go onto any popular chess website and I'll analyze your game for you and tell you exactly what you've done wrong and how bad you are at chess. So here's the goal of this talk. I want to teach you how to build game engines for pretty much any game that works a little bit like popular strategy games. I want to do this by kind of following the history of how this game development thing happened. I also want to show you the best technique for the job, because there's multiple ways to get this done. But I also want to do it in a general sense, because a lot of information you'll find about game engines is mostly about chess. So I want to talk a little bit more generally and not give you Bawo-specific information or chess-specific information. I am going to use chess as an example a few times because I think people understand chess a little bit, but I'm going to try and be as general as possible. So there are some prerequisites because it turns out if I didn't put some prerequisites on what we'd be talking about, we'd be here until the conference ended. So the game must be 2 players. This means it's not Monopoly. I'm not playing against 5 people. It's me versus the computer. Next, it must be 0-sum, which means we can't both win, we can't both lose, or we must both draw. Basically, my win is your loss. Winner takes it all. It must be turn-based, which means it's not a game of snap. It's not about how fast you can play that gets you your turn. It's about I turn, you can think as long as you like, then your turn. It must be perfect knowledge, which means it's not a game of battleships. Everything that I know, you need to know too, and vice versa. And it must be non-random, no dice rolls. I realized Bawo fit this example, and despite how restrictive all those things sound, it turns out most popular strategy games fit this. Here are some examples, chess being a popular one, shogi, gomoku, Go, Connect 4, tic-tac-toe, and of course Bawo. And once I realized this, I realized I had exactly what I needed to make a computer absolutely destroy me at the game. So I'm not interested in lecturing you, so if I were to teach you this game, teach you no strategy, what's your first idea on how to play a game of Bawo? You have no idea how to play it. What's the plan? Yes? Yeah, give it a shot and go. So that's our strategy number 1. We are going to play an absolutely random game. So this is Surprisingly easy to implement, in case you couldn't realize it. Statistically, it could play the best moves you've ever seen, better than any engine will, and it is a useful idea later. The cons are everything else. Random is pretty much guaranteed to never play what you want it to. Here's some pseudocode. We're doing pseudocode this talk. Enjoy the simplicity while it lasts. It gets a lot worse from here. Okay, so we're done playing randomly, and I've beat you 3 times now at a game of Bawo. Now, all of a sudden, you've got a bit of a feeling watching me play. A bit of a gut feel for the game. Our next strategy should just be to play moves that sort of look good. This is easy to do if you're a person. It's called intuition. And typically, it's a strategy that results in some not terrible gameplay. You can start looking competent playing your game. And it's the basis of better ideas to come. So, as an example, consider the following chess position. If I move the queen over here, there's something wrong gut feel-wise about this position. Putting your queen in front of an enemy pawn is pretty much never a good idea, no matter what you do. So this just tickles our intuition the wrong way. However, giving a check is typically a pretty good thing to do. So intuition-wise, giving the check is probably something you're going to want to do. So that's this intuition feeling we're talking about. So here's how we're going to do it on a computer. We're going to define a mathematical function, or a computer function. We're going to define a function that takes in a board position, or a game position, whatever, in terms of the side to play, and it yields a number. The bigger the number is, the better. And this is going to emulate our human intuition. If the number's really big, it means it's got a good gut feel. If it's really small, it doesn't pass the vibe test. So we check every single child in our position, all the possible moves we can make, and we pick the one that gets the best evaluation. So here's an example for a game of Bawo. We have 4 children here. You can see the one on the far left is rated -199. This one is not rated too well. It's probably not going to do too well for us, so we're going to avoid playing that. The one right of it is rated 0, so it's a data equal. So if we want to play for a draw, we can play that one. The next one over is rated 5, so it's a slight advantage for us. And the next one is rated the quake fast inverse square root constant, which is around 1.5 billion. Needless to say, that one is rated very highly. It passes the vibe test. We're going to play that one. So this is a bit easier said than done. To make this evaluation function, we need to understand what is good. This means we need to understand the game we're playing. For many games, this is very well understood and very complex. For chess, you've got things like material, king safety, mobility. There's a lot of factors. For Bawo, unsurprisingly, there aren't very many online resources that I could find. So I had to do my own experimentation, and I have come to the very scientific conclusion through about a year of experimentation that nothing beats just a straight material difference. Therefore, the person on the top here is doing quite well for himself at the moment. Okay, so here's the algorithm for it. We generate every single move we can. We have some temporary best move variable and some best score. We duplicate the position we're interested in and make the move so that we get the position after we make the move. We take a look at our score, and if it bests our current score, then we say our best move is that new move. And then at the end of our search, we return our best move. So now we've played a couple of games of Bawo against me. You've gotten a little bit better. And now instead of just thinking about what you can do, you want to consider what I can do in return to you. Because it's a strategy game, we're taking turns. Considering what your opponent is a good idea. So for example, if we take a look at our previous position, but now if we take a look at the one with the quake fast inverse square root constant, it comes down to a board position that's rated 500,000 for the opponent. If it's rated 500,000 for the opponent, that means it's not rated very well for me. That means that this node over there isn't really 1.5 billion-ish. It's more like -500,000 because our opponent has a move that can absolutely decimate us and give them a really good rating. Now, the computer science majors among you might be beginning to recognize this sort of structure. Some big bulbous thing at the top with little tendrils coming off it into things that spawn more tendrils. Yes, this is beginning to look a lot like a tree. Yeah, there we go. Got it. Yes, this type of tree. So it's beginning to look like a tree, so we're going to do something called a game tree search. So here's the idea. We're going to take a look up to a certain depth of your turn, my turn, your turn, my turn. At the end of it, we're going to call our evaluation function. We look at every single possible move combination, and once we're done, we propagate the results up the tree somehow to choose the evaluation for our root position and basically rank all of our children, and we can figure out which one's the best to play. Now, the key thing to notice here is that if you're me and you want to win, you're going to choose the evaluation that is maximum, maximizing your score because that does better for you. However, if you're the opponent, you're going to want to minimize the score as much as possible because me doing worse is better for the opponent. This sort of minimizing, maximizing shuffle gives the algorithm the name minimax. Here's an example of a minimax tree. Black means it's the opponent's turn to move and they will minimize the score, and white means it's our turn to move and we're going to maximize the score. So over here we have this is our root position, and we have two legal moves we can make. Then the opponent on this legal move has two legal moves they can make, so on and so forth. We search depth first, and we come to this node here. We reach our depth limit, and we take an evaluation, and we evaluate here. Since it's our turn to make a move, we get to choose between making this move or this move. We want to make the move that gives us the best evaluation, so we want to make this one, so this node here is rated 4. We do the same on this one, and this node comes out to be rated 6. Now, however, our opponent's going to want to make a move that puts us in the worst position possible. So he can either put us in a position that is worth 6 or worth 4. Now, he's going to choose the one that puts us in a position worth 4, because that means he does better because we do worse. The same thing happens on this side, and over here, eventually we come and we find the evaluation for the position. So, minimax game tree search. This is actually a very easy algorithm, even though it doesn't look like it when I'm hovering my mouse over a drawing. It will play with pretty decent strength on most games as long as your evaluation function guides the tree search correctly, and it's the basis of many better ideas to come. It's also got another hidden advantage over some later algorithms, and that it's extremely memory cheap. We're going to implement it recursively, so it means that we can actually use very little memory when doing this. However, the game tree gets big very quickly, and choosing the depth we want to search to is quite a hard challenge. However, we will fix those problems when we get to them. So here's the algorithm. You don't have to look at it too closely because it's quite disgusting. Instead, what we actually really want to do is simplify this. You as software developers know that if you see something that looks similar in a line of code, there should be some way to simplify this, and there is. So let's make a note about the games we're interested in. If we're interested in zero-sum games, we should make the observation, your win is my loss. This kind of mathematical relationship where the min of two numbers is the negative max of their negatives. We can basically reduce the complexity of our algorithm using this fact, and this creates an algorithm called negamax, which looks something like this. The specifics aren't really important, and it does the exact same thing as a minimax game tree search. The only difference is the code is a lot simpler and a lot cleaner. So we should make some notes about minimax. Minimax and derivatives algorithms are kind of brute force algorithms. They just kind of check absolutely everything they can. So the faster all your code is, the deeper it can search in the same amount of time. So therefore, everything you can should be optimized for speed. So if your game playing code is really slow, now's the time to optimize it to hell and back. So it was at this point where I started implementing it for Bawo that it started to become really, really hard to beat. In fact, it became impossible to beat. However, there are still things we can fix. Take a look at this graph. At the bottom of our tree, we have our leaf nodes where we take an evaluation. The blue dots are the actual amount of leaf nodes in a minimax game tree search that I've found. And a red line is just them interpolating. Now, I'm not sure if you can see the scale of the graph, but it goes really quickly. 15 moves in, we're looking at like almost 1.5 billion different leaf nodes. So we're going to hit a very large computational disadvantage very quickly. We can do a log plot of the same thing to see that my line interpolates the points quite well, but it grows very, very quickly. The complexity of a minimax algorithm is O of b to the p, where b is the branching factor and p is the depth. The branching factor is the average amount of legal moves per position, which kind of makes sense. Bao's branching factor is about 4.09-ish. So that means in every single Bao position you look at, there's on average about 4 legal moves. This means 20 moves in, we're looking at 1.7 trillion different leaf nodes, and after an average 60 move game, that's 5 undecillion leaf nodes, or 5 times 10 to the 36 leaf nodes. Needless to say, we're hitting a computational buffer really, really quickly. However, most of the nodes on this tree are vastly, vastly uninteresting, and we don't care about half of them in the way that they're an instant loss for us or an instant loss for our opponent. If they're an instant loss for us, we don't want to play it. If it's an instant loss for our opponent, they're not going to want to let us play it. So it'd be better to remove the search of a few nodes that we're just wholly not interested in. Introducing alpha beta pruning, the greatest thing since garden shears. Please laugh. It has the possibility of reducing our tree search complexity to O of square root b to the p, which means we can literally go twice as deep for the exact same amount of computing power, and it is a completely non-invasive algorithm. This means we are guaranteed to get the same results for free. The speed improvement comes at a hindrance of absolutely nothing. So here's how we're going to do it. We're going to keep two bounds on the score of our current node, alpha and beta. Yes, very creatively named. Alpha is the minimum score that we are guaranteed to get. The maximizing players is us, the one that's making the move, and it's the minimum score we're guaranteed to get. Our root position is at least this good, and vice versa for beta. It's the maximum score that the other player will allow. If we got a position that's bad for us, and alpha guarantees that we have something beta a little while back, we can just stop searching the worst position because we know we have an alternative to play, and vice versa for beta. If we have something so good and our opponent has a refutation, they're not going to even bother letting us play the good move. The thing to remember is that one player's upper bound is the other player's lower bound. This is how it works in our recursive algorithm. So here's an example in chess. I'm going to cut out the really massive tree search on the node on the left, but after a long and extensive tree search, we come to the conclusion that that node on the left is hunky-dory, and we are absolutely going to consider it. Then we do our depth first. We come up to the root position. We go to the next legal move we can make, and we look at the moves our opponent can do. Now, our opponent has a way to capture a rook. This is bad. Now, it might not be the worst thing our opponent can do to us here, but it is a bad thing for us. And we know we have an alternative we'd rather play. So we don't have to consider the move where he captures our queen, because we already have something better, which means we can just forget about searching the rest of that entire node. And that means we can forget about that entire node too. And this saves us one whole evaluation cycle on that bottom right board. Now, this seems small, but this is just because it's a small game tree. As we get to hundreds of thousands of leaf nodes, these optimizations start adding up very quickly. Well, just how quickly? Here's the original graph. I'm going to plot a green line at the bottom that shows you exactly how many leaf nodes we get in a perfect alpha-beta scenario. It's pretty good, isn't it? If I do a log plot, you can see it's leagues less steep. The thing to notice is that this is still exponentially increasing. You can't do anything to get rid of that. However, it is exponentially increasing so much slower. So it's a great improvement. Of course, nothing is for free, and we have our caveats. The improvements only happen if we search literally every single good move first. So we need to come up with some other move ordering strategy. Since the whole point of our tree search is to find good moves, currently we've got a little bit of a chicken and an egg problem. So we've just got to find a heuristic that kind of somewhat puts the beta moves first on average. Now, the reason we do this is because if we searched backwards, the bounds would not be set. If we don't get them set, we get no cutoff. So if we take the previous example, if we consider the one where we capture first, our opponent captures our rook and then captures our queen. We don't have anything better, so this just might be as good as it is. Only later do we realize that actually we have a really good move we could have played instead, so we get no cutoffs. So if we order it backwards, nothing good happens. So you need to, on average, kind of guarantee that you put better moves first. So here's the pseudocode for that. Notice once we hit our depth limit, we take an evaluation of the position, we generate our moves, and now we have some sort of ordering heuristic that's specific to your game. We check every single move, and if it bests our beta, which means it's so good our opponent would never let it happen, we return the value because we can just stop thinking about it entirely. And if it's better than our alpha, then we can say we have a position that is at least this good, and we can remember this for later. And once we're done with our search, we return alpha. Now, to make a move, we need to start with an initial alpha and beta, and what we do is we consider every single root move in our beginning position. We evaluate it with infinitely wide bounds at first that constrict as we go down the alpha beta search, and if that score does any better than our previous scores, we just set the new best move to that move, and we return our best move. Brilliant. So this is our first improvement to Minimax, the alpha beta game tree search. This is still very easy to implement. In fact, the pseudocode pretty much fits on one slide, so I'm proud of that one. It'll play with pretty decent strength for most games as long as your evaluation function is right, and it is still incredibly memory cheap. However, it's got some drawbacks. It suffers on games with really high branching factors, like Go, where there's like on average 150 moves per position, so it's not going to play those games very well. We can still make improvements because this is still not the pinnacle of it, and it still relies on this evaluation function thing. And that depth variable is still giving me a heart attack every time I think about what I need to set that value to. And as a few of you might have noticed, if we're only searching so deep, there might be a good move out of reach that we don't see. This is called the horizon effect. To make a very long story short, it's a bunch of effects, but the most commonly hindrant version of it is when we see a move, we decide that it's an amazing move and we play it, and then only later, because once we played a bunch of moves and we can see a little bit deeper, then only do we realize that the move is absolutely horrible and we shouldn't have played that in the first place. and now we're stuck because our engine has played something really, really bad. Therefore, we play the wrong line, believing it is good when it is actually really, really bad. And to see these bad lines from the good lines, we need to search deeper, and searching deeper requires more computation power, and it's another chicken and the egg problem. However, not all positions are really susceptible to the horizon effect. Quote-unquote quiet positions, where there are no back and forth exchanges of material or tactics or basically anything tricky. If there's a position where you can basically play anything and be roughly okay at the end of it, they don't suffer bad from the horizon effect. So what we should do, instead of evaluating at the end of our search, is we should do another smaller search and just search these turbulent positions until we hit something quiet. Introducing the quiescent search. Lovely word, that. At the end of a regular alpha-beta search, we're going to perform a quiescent search, and this just looks at captures or whatever's turbulent for your game, because not all games have captures. It doesn't look at every capture possible, otherwise the tree search would never end. So instead we place an evaluation bound on what we're going to search, called a standing pat. Basically, if you're playing chess, if you win a queen at some point and then you lose a pawn, losing the pawn isn't material and you can just kind of forget about it. So, adding a quiescent search, it's got everything great about Minimax, however, it pretty much destroys the horizon effect. And the pseudocode for the quiescent search looks like this. This doesn't replace our original alpha-beta search, it just replaces the evaluation for it. We find our standing pat, check our bounds, we generate all the moves that we are interested in, all our turbulent moves, and we just perform another regular alpha-beta search, and life is all good. So another thing a few of you might have thought about if you play chess is there might be multiple ways to reach the same position from different lines of play. For example, playing the queen's pawn or the king's pawn first in chess, and you get to the same position where all the pawns are in the center. Now, if you come along the left path and you evaluate it fully and you figure out what that bottom position is, coming from the right path, you'd want to reuse those results because it's the same position. However, our current tree search won't do that. This is called a transposition, and transpositions show a really bad waste of our time because we research things we've already done. It would be nice if we could reuse the results from a search that we've already done if we find a transposition. And what we'll do is we'll do exactly that. We'll store transpositions in something called a transposition table. It's a really specialized hash table, which means we need a way to take a board, generate a hash, put it into our table. This hashing is normally done using an algorithm called either Zobrist or BCH, but that's game specific, so I won't dwell on it. So we generate a hash of the board, take a module of the hash, check the table. If it's there, return it with some conditions. Basically, it's a really large and specialized cache. We're interested in speed here, so we're not afraid if we overwrite some data at some point, just so long as, on average, we're hitting more than we're not. So, of course, there's caveats. With alpha-beta search, we pretty much never know the exact evaluation of the node, and this is due to our pruning. We only really know if the node's exact evaluation if it's the agreed-upon principal variation that both players will play, or if it's so bad that we don't consider it because our opponent has something better, or if it's so good that we're not going to consider it. Basically, it's at least this good or at least this bad. So we get three types of nodes: principal variation nodes, the path of play for both players; cut nodes, the result of alpha being changed. Basically, our score is at least this good; and all nodes, despite that absolutely horrendous naming, it doesn't mean every node, it just means the node that is a result of a beta cutoff. So our transposition table needs to keep track of these types of nodes, that when we query it, we make sure it falls within our alpha and beta bounds. So here's the algorithm for this. We generate a hash of the board, take a look at our transposition. If the hashes inside of the transposition entry align and the depth is greater, the reason we check the depth is because the deeper we go, the more accurate it is. We don't want to reuse less accurate results than what we're going to get. If it's a PV node, if it's exact, we just return the value wholesale. If it's the result of an all node or a cut node, then we have to check the bounds, and otherwise we just say it's not there. And then inside of our search, we just query the transposition table, check if it's there, and if it's not, we continue on our search, and then when we're done with our search, we can just insert it into our cache and be done. So, transposition tables, all the previous pros, plus we're not going to research positions that we've already put effort into. In Bawo, this is a little bit more minimal because Bao's quite turbulent and recurring positions don't happen a lot, but in games like chess, it's vital. So, we're going to finally dwell on the depth problem. How much depth? 5 moves, 10 moves, 15, 60, I don't know. The ideal thing would be to just set a timer on it and let the algorithm decide how far it can search in that time. Introducing iterative deepening. It turns our search as it stands into a breadth first search. Instead of a depth first search, we just search line by line by line until we hit a time limit. And we do this by searching 1 move deep, 2 moves deep, 3 moves deep, 4 moves deep, iterating the depth. You see, that's where the name comes from. They're very creative, these people. And now this sounds like an absolutely horrid waste of time. However, the reason this works is because we've done a lot of our searching before, and we can store our results in the transposition table, and we end up not wasting a lot of time. And so this doesn't change our search, it changes our thing that calls our search. The only difference here, as you can see, is we start with a depth 1 and we iterate until our maximum depth, and now we have a timer. Wonderful. So adding an iterative deepening search just means we can let the algorithm go as long as we let it, and it will return a good result, and we don't have to worry about setting a depth variable anymore. Wonderful. So I could see Rob was glaring at me like he was some old-timey cartoon character willing to swap my feet out from me with a cane like in Looney Tunes, so I'm going to cut the rest of this short. There are some other improvements. One of the most obvious of them is multiprocessing, because if you can't make an algorithm better, just chucking more compute at it will always make it do better. Other important ones, principal variation search, which gets rid of moves from our move ordering which we think are bad. What the chess people call mate distance pruning, also very powerful, and other types of search extensions and reductions. So now, I've talked a lot, but now the question is, what can it do? Well, here's a Bawo board on a computer, and I'm going to play Bawo against my own machine live. I had to write this for school, and I want to show you, I've written some debug output for you too. Here you can see the depth it reaches in the iterative deepening cycle, and it tells you the score, the evaluation score at the end of it. A score of 0 means it's a perfect draw. This 2000 here means it thinks that after 12 moves it can be 2 beats up, but right now it thinks this position's dead equal. I'm going to play this. And as you can see, I've already made a mistake. It now thinks after 13 moves it's going to be 6 beats up. So I'm going to capture this. Another mistake, 14 beats up, and it's absolutely ruined me here. I'll capture here. So that hasn't made things worse for me. It still thinks that we're 12 beats, and as you can see, it is very close to emptying out my front line, so I think I should refill that. I'll capture here. And another mistake. Now it thinks it's going to be 22 beats up, and you can see it's wiped out my front row pretty much entirely, so I'm doing very well at the moment for myself. So I haven't made things worse, which is a good thing. It's still thinking 22 to 24 beats. I don't know what to do here. Okay, I haven't made another mistake, which is always good. I'm going to capture here. I've made things slightly worse, still 24-ish. I'll play here. Still 24, so for a computer play, this is quite good. I haven't played this well in a long time. Oh, that was a mistake. 32 beats. So I'm losing with flying colors right now. I haven't made things worse, which is lucky. Let's do this. Oh, and there you go. It emptied out my front row because I made a mistake, and it was over for me. Nothing I could have done. So I didn't try my absolute hardest to play against the machine because, again, Rob, Cayden, Looney Tunes. But the machine would have beaten me no matter what I did. The machine can see anywhere from 14 to 25 moves deep, depending on how much time I give it, the position, and how fleshed out its transposition table is. As a human who's played Bawo for a long time, I can see 1 to maybe 2 on a really good day. The computer is so good that a simplified version of Bawo called Bawo la Kunjifunza, you don't have to memorize that name, there's not a test, that doesn't have hands and is a little bit easier, and they teach it to beginners. It found a 21-move forced sequence in under 0.8 seconds. That means if the computer goes first, it is guaranteed to win no matter what you do, because there is a sequence of moves where you can only last 21 moves or worse. I can't overstress this enough. 0.8 seconds to find a 21-move deep win sequence where you can do nothing to refute it. I tried to do this before I did the improvements with just pure alpha beta, and it took it hours to reach depth 17. So as it turns out, the improvements do something, and yeah, 21 moves, there's no refutation. A little interesting side point is you notice that the lines of play there, they don't form a perfect triangle, as one might expect from going exactly 1 move deeper. That's the result of our quiescent search, searching slightly deeper than what we tell it to. So now this is all hunky-dory, but let's talk about another way we could perhaps do this, a more modern technique that changed the world, honestly. So that random play thing, oh yeah, I'm bringing it back, people. So let's make an observation about random games. If I were to take a chess position where white is winning and put 2 chimps on either side of the chessboard and have them play random chess moves, more often than not, white would win simply because white was winning in the initial position. So we can use random games as some sort of evaluation function of sorts, to emulate a winning chance of a given position. And this forms the basis of a technique called a Monte Carlo tree search. Monte Carlo, like the casino. So here's a graph of it. Here's the idea. We have a tree, and we're going to choose a leaf node to search down. There's some heuristic algorithms to this, or you can do this randomly, but this is normally done using something called UCT. So we choose a leaf node to search down. Then we expand the leaf node by adding its children. We run a random simulation on that new child, and we propagate that result back up the tree. So I don't want to dwell on this too much because, again, Rob, Looney Tunes. However, it does have some very interesting properties. If you implement it with the right UCT stuff, it is actually a best first search, not breadth first or depth first. It'll heuristically try and search the moves it thinks is best first. And it should be theoretically as good as minimax-based algorithms, but the thing that distinguishes it is that it can play large branching factor games like Go, or games that, just have a lot of legal moves per position. It's a bit newer than Minimax, and a lot of research is being conducted into it, because we'll see later why. And here's the kicker. It has no need for a built-in evaluation function. In fact, it doesn't even really need any pre-built knowledge of the game at all, although it does help if you coax it along the right route a little bit. So it does have some drawbacks. It will eat your memory faster than running Chrome and VS Code at the same time. It is a memory-hungry algorithm, because unlike alpha beta, which can be done using recursion, every single one of those nodes is a chunk of memory you have to allocate and keep track of. So this consumes memory really, really quickly. It also has a tendency to kind of miss the forest for the trees in specific positions, because remember, if you're evaluating something randomly, it kind of just does the average of things. There might be one very specific line of play where if you play it, it absolutely wins, but everything else is dead lost. So it's like the position is winning, but only if you play this. And Monte Carlo tree search tends to kind of miss that a little bit. And there's also not as many resources on it as Minimax-based algorithms if you want to go and build one yourself. So to compare the two quickly, Minimax is very brute force. It just checks absolutely everything you can. It relies on great speed and pruning for you to get a reliable result. Monte Carlo tree search tends to search along more promising lines first and kind of discard what it doesn't like. The algorithm can be a bit slower than Minimax, but it makes up for it by being smart. To put it very simply, Minimax is stupid faster. And it turns out that's a reliable way to play for certain types of games. Now, I have a legacy of being a little bit old-fashioned, I think. I still write all of my code in C because, Java's just not for me. And so I want to beat that legacy a little bit here today. So I want to think about that evaluation function problem a little bit. Evaluation functions based only on material and human experience where they've researched and tuned it by just randomly poking things, or move ordering solely based on some functions that humans designed and kind of just thought, look good over the long time of history. This feels very odd if you ask me. So we could do like some machine learning here or something. I mean, since humans are already poking and prodding randomly and expecting random results, why don't we just have a machine do all the hard work for us? So Monte Carlo tree search doesn't rely on an evaluation function, so let's just train a model to emulate the output of a Monte Carlo tree search and call it great. We could also do this because Monte Carlo's tree search ranks its moves almost heuristically as a part of its algorithm. We could also use this to improve move ordering. And so I did. I tried it. Here's a confusion matrix of my results. In theory, if the model was perfect, it would be a perfect diagonally straight line from top right to bottom left, where the predicted results of the model align exactly with the actual evaluations of a position. It hasn't quite done that, but you can see it's not bad. It has learned something. It didn't turn out great, and it turned out it lost pretty much all the time to my original algorithm, but I think this is my fault. This technique of training a neural network to output the evaluation of another engine is used by Stockfish, pretty much the greatest chess engine available, although The difference is that the Stockfish people use very specifically designed fast neural networks to be able to run the neural network faster. Because remember, if you run it slower, you can't run as deep, and if you can't run as deep, you can't see the tactics as deep. Now, I couldn't run my things as deep, so therefore it just lost that slight competitive edge against the advantage, and it didn't play better. However, we can apply this move ordering, rank, and evaluation thing to Monte Carlo tree search. And speaking of artificial intelligence, this is how Google's /DeepMind's AlphaZero works. All it is a Monte Carlo tree search with a neural network attached that has two heads, a policy head, which is basically bettering your move ordering for the Monte Carlo tree search, and a value head, which replaces the random simulations with the output of a neural network. The thing is taught using self-play, and this is the technique that finally beat Lee Sedol at Go. And that's what they were talking about in the keynote this morning, so it all comes around. And speaking of DeepMind, it turns out that games were what originally got Demis Hassabis into programming, the founder of DeepMind. And as it turns out, the same techniques, or ideas, should I rather say, to play games work for many other problems, such as Demis Hassabis' protein folding program AlphaFold, or balancing the data loads on Google servers, which just saved them astronomical amounts of money. And so it turns out this random little curiosity of playing a board game is a very interesting skill to have if you can learn it, because it turns out playing games is very similar to other problems. It's adversarial and rule-based. So if a game is adversarial and rule-based and other problems are, maybe you could think about doing stuff with games. So here's some resources you can look into if you're interested in doing this yourself. The Chess Programming Wiki, despite its name, actually has quite a couple of good resources for things that aren't chess. A lot of it is chess-centric, but you can warp it to any game you like. The original AlphaZero paper, if you're really interested in the newfangled ways. The Stockfish source code, if you really want to research minimax algorithms. And if you're really interested in chess and you don't give a damn about what I have to say about the beads and holes board game, you can watch Sebastian Legu's excellent video series on his attempt to make a good chess bot. And the possibilities here are really limitless. My restrictions were there because I like strategy games, because I always lose at probabilistic games, because luck is never on my side, and it's not just because I suck at playing games. So it turns out, because of the way Monte Carlo tree search works, it's actually quite robust for random games. So playing poker or Durac or bridge even is very possible with Monte Carlo tree search. And there are many brand new tree search algorithms that you can go and research that might have some advantage in a game you're thinking of besides Monte Carlo and Alpha Beta. The possibilities here are limitless. As long as you open your mind to what you can do and you find the right techniques, you can make a computer beat you at anything. I'd like to say thank you very much for attending. Please remember to vote. I believe you can win some pretty cool stuff if you vote and you get chosen. Share your creations. Don't leave any game unsafe from your awesome engine programming powers, and make sure that humanity doesn't ever win another board game ever again. If you have any questions, although I'm not sure you do, you can come and ask.